Okay, now let's talk about capacitance. So we know that in a cell, we have two conductive regions of fluid, separated by an insulating membrane, with a voltage across either side of the membrane. If you've had some exposure to physics or electronics, you'll perhaps recognize that this arrangement is basically a capacitor. In electrical circuits, a capacitor is a circuit element that can store electrical charge, and usually consists of two conductors separated by an insulating region called a dielectric. When a voltage is applied across a capacitor in an electronic circuit, charges line up on the two plates opposite each other across the insulator, opposing the applied voltage. This charge accumulation continues until the plates are effectively saturated, at which point the voltage across the capacitor is equal to the applied voltage. When we apply a voltage in a step, we see a characteristic charging profile. The key point for our purposes is that the storage of charge on opposite plates slows down the change in voltage across the terminals of the capacitor. If we step back to the original voltage, the capacitor slowly discharges, going back to the original voltage. Again, the capacitor is slowing down the change. Basically, you can think of the capacitor as buffering voltage changes. If you're used to thinking about electronics, then this should be a fairly familiar concept. If you're not, never fear. The concept of capacitance is pretty straightforward, and a lot of familiar physical systems show analogous behavior. For instance, a particularly familiar analogy is heating something up. If we take a plate of metal and heat it up with this blowtorch, it doesn't just instantaneously jump to the temperature of the blowtorch. Rather, the heating curve is basically the same shape as the capacitor's charging curve. When we remove the heat, we see that the plate doesn't return to room temperature immediately, but instead cools off slowly, basically following the same shaped curve as the capacitor's discharging curve. Obviously, the heating of the metal plate has nothing to do with charge, and the function of the capacitor has nothing to do with heat. But the similarities between these two processes do have a reasonably deep physical connection at the level of the differential equations governing their behavior. Oh yeah, and our water analogy from earlier works here too. In this case, the capacitor is like a flexible hose or balloon in the system. The flexible bit can balloon out, making the water pressure ramp up slowly until the system is fully inflated. When we shut off the flow of water, the inflated balloon can release water, causing the water pressure to turn off less quickly. It's a little bit messy to measure, but the charging and discharging curves for the water pressure look just like the capacitor voltage charging and discharging curves.